This is lecture 2.4 for Psych 440, Effect Sizes and Significance. This lecture is a little bit of a tangent from our main theme in this module. We're talking about some things that aren't covered in your textbook, but that are very, very important for you to keep in mind because we're going to be looking at a lot of correlation coefficients over the rest of the course. You may have been taught in your statistics courses or your other research methods courses how to tell whether a correlation is significantly different from zero or not. But when we talk about correlations in IO psychology, that's not the only thing that we're concerned about. We're going to be concerned with something called the effect size, and unfortunately, we don't have simple, easy rules like is the p-value less than 0.05 in order to determine whether those effect sizes are meaningful. We have to use some contextual information. So I want to talk a little bit about how to do that so that as you're going on in the course, as you're looking at different kinds of correlations, you're able to put them in an appropriate context and interpret them accurately. Basically what we're concerned with here is the question of, well, how big, how strong does a correlation need to be in order to be meaningful? If you remember from the last lecture, we talked about how correlations that are closer to +1 or closer to -1 represent a stronger association. We can better predict one variable from the other when we have a large correlation. But that kind of leads us to this question of, well, how large is large enough? What kind of a correlation is big enough to care about? Now, you were probably taught in prior classes that a correlation is significantly different from zero. That is, we can be pretty confident that that correlation really does exist if it passes a significance test, if the probability that we would obtain that correlation, if the null hypothesis were really true, is less than 0.05. The problem with this approach is that with many different kinds of statistical tests, and with correlations in particular, whether or not you get a significant result is very much a function of your sample size. In other kinds of statistical tests, there are more pieces to it than that, but when we talk about correlations, the significance value is a very direct function of the sample size. So to give you a practical example, a correlation of 0.15, not too close to 1, pretty small, but in the positive direction. That correlation of 0.15 is statistically significant if we have a sample of 173 participants. If we have a sample of 172 participants, that correlation no longer meets our criteria for statistical significance. So this should maybe trouble you a little bit. There's a lot of debate in the broader psychology community right now about whether significance testing is really the best way to examine whether our hypotheses are supported or not. There's more debate than we can go into in the context of this course, but if it seems a little wrong to you that whether our findings are significant or not could swing back and forth based on the presence or absence of one person in our data set, we call that the effect size, and we can calculate effect sizes for different kinds of statistics. Correlations tell us how strong is that relationship. a correlation that's closer to 1 or -1 is a larger effect. You may also see sometimes we can square the correlation coefficient and use that as an indicator of that percentage of variance explained. Now, something to keep in mind here. Correlations can't get any bigger than 1 or -1. When you square a decimal number, you might remember from like 8th grade algebra, that number gets smaller. So our R² values are always going to be smaller than our correlations. When we're comparing groups, you'll see people refer to a statistic called D, which is a standardized measure of the difference between those groups. Larger D values mean a larger, stronger, more impactful effect. So when you see, and the nice thing about D's and R's is that they're have to apologize here. That one is a trick question. There is no correct answer. The answer is, it depends. We're drawn to those big numbers. We'd love to say that we've got effects in the 0.6s. In some lab studies where we're comparing very straightforward things, sometimes we do get those effects. But very often, in I.O., again because we're studying such complicated things, we end up being happy with much smaller effects. So I want you to consider a scenario here. Imagine that you are a researcher studying cancer treatments. You develop a treatment for a new, not very well understood form of cancer. And right now, out of every 1,000 people who are diagnosed with this form of cancer, if they are not treated, 600 out of 1,000 people will die, and 400 out of 1,000 people will live and recover. In your clinical trial with your study, you find now of 1,000 people diagnosed with that cancer who got your treatment, 600 of them will live and 400 of them will die. Think for a minute. If you were diagnosed with this cancer, you'd probably sign up for the treatment, right? We made a difference here of 200 lives out of 1,000 saved. It's not perfect, but it's certainly better than the alternative, right? Well, now, if you have a piece of paper handy, jot down, what do you think the correlation is between treatment and survival? Make your best guess. These data lead to a correlation between treatment and survival of 0.2. If we square that to get our percentage of variance explained, we've only explained 4% of the variance in this scenario. Probably on that Zaption question, most of you didn't pick 0.2 as a very impressive effect size. In this scenario, though, it could make the difference between life and death. So a very small statistical relationship can have a very big practical impact when we're talking about a complex phenomenon. Some comparison values for you. You may have heard that most doctors recommend that people who are at risk for heart attacks take an aspirin a day. The correlation between taking aspirin and reducing your risk of a heart attack is 0.02. That's not the squared correlation, that's the correlation. That correlation is statistically significant. It's been found to be different from zero because it's been studied in trials with thousands and thousands and thousands of people. So here's another example of how even a very tiny correlation could be statistically significant if you've got enough people in your sample. In this case, the reason that doctors continue to recommend this based on this tiny little correlation is because taking an aspirin is inexpensive, it's fairly low risk for most people, and it has this tiny benefit for predicting a really horrible outcome. So in light of the context, in light of the stakes, that relationship, although it's tiny, it does make a difference for a handful of people. Some other well-known correlations. You're probably aware that consuming alcohol is associated with greater likelihood of aggressive behavior. That's kind of conventional wisdom. Everybody knows that. That correlation is 0.23. A widely observed finding. It's been replicated many, many times. This is actually an estimate based on a meta-analysis. This thing that everybody generally believes to be true, it's still not a perfect relationship. And so this gets at the idea of understanding context. We're trying to predict something that's complicated. Aggressive behavior is complicated, there are situational factors, there are lots of pieces of the puzzle other than alcohol consumption. In IO psychology, and in lots of areas of applied psychology in general, we don't ever expect to explain all of the variance in our outcome with just one thing. We're going to work to build up pieces and understand parts of the contributing factors. Most of the things that we're interested in studying don't have just one cause. And then one last piece of comparison for you. The correlation between latitude, or nearness to the equator, and the average daily temperature, that's only 0.6. There's no subjectivity in here. We can measure both these things very, very well. This is a good, hard science kind of a finding. Even there, the correlation is pretty far from perfect. So when you first start learning about correlations, I see many students feeling very dissatisfied when we're talking about correlations in the 0.2 and the 0.3 range, because they seem like they're really far away from 1. The point I want to make here is that even things that aren't subjective, aren't based on perceptions, even things that we know, there's a geoscience basis for this relationship, even there, it's not a perfect relationship. Other factors come into play, like how close you are to a coast, weather patterns, some other things in there. So as we go on to interpret correlations, this doesn't necessarily mean that any correlation of any size is always fine all the time. Whether we're going to consider an effect to be big and useful or small and unimportant depends first of all on how does it compare to other things. If I come to you and I say I have this new selection test that predicts job performance with a correlation of 0.5, well, that doesn't sound like much, right? I'm only halfway to 1, but the very best selection tests we have generally aren't much better than 0.5. If I came to you with so that's going to be a good selection test. It's at least as good as whatever else is out there. If I came to you and said, oh, I've got this great new selection test, I got a correlation of 0.15, that's not nearly so impressive because we have lots of other predictors that predict that outcome as well or better. We're also going to so that's going to lead us into our next topic, which is psychological measurement. How can we be confident that the measures we're using are really getting at the thing that we want to study?